All right, well, was out sick for one day, had technical problems the other day. We're in a new classroom just temporarily because the AV wouldn't work on the other one, and so sorry we don't have a whole lot of time. We're gonna have to kind of rush through things here. So the homework that was due today was postponed till tomorrow, right? You got the email. So what we want to do today is talk about a new addressing mode, indirect addressing. So first let's review what direct addressing is. With direct addressing, the operand is the operand specifier is the address in memory of where the operand is. And so the assembly level 5 letter for that is a lowercase d, and you've done programs with that. And that's direct addressing. Now this next addressing mode we're going to learn is called immediate addressing. Now let's contrast immediate with direct. With immediate addressing, what happens is the operand specifier is the operand. Now just think about that for a minute. The operand specifier is the operand. In other words, the operand is available immediately in the instruction itself. The data is part of the instruction. It's there immediately in the instruction. You guys see what we're saying? Okay, so look, here's how it works. Here in figure 5.10. So normally when we, in our first program, when we output the two letters HI, we stored the value of H after the stop instruction. And we had to know where it was in memory to access it with direct addressing. But now the letter H is not stored after the stop instruction. The letter H is stored what? As part of the instruction itself. Do you see? So let's, in figure 5.10, the first statement is load byte accumulator H, immediate, single quotes around the big A, capital H. And then store byte accumulator to the output device. That still uses direct addressing. And then load byte accumulator, the I, quote, single quote I, that's a single character. So that is part of the instruction itself. And then store it to the output device and then stop and end. And so we don't have to store the H and the I after the stop. Does everybody see? And so you run this program, the output is high. So let's demo that. Okay, so here's our demo. We went to the help system and copied to source. So here's the program. Now watch what happens when we build this. Before we run it, let's build it. And when we build it, as usual, what we get is the object code here. But then we have a nice formatted listing here. By the way, you guys, I've noticed that some of you need to do format from listing before you hand in your exercises or your programs, please. See, remember that's edit, format from listing. Okay, so so look here in the assembler listing window. Here's the load byte accumulator, capital H, single quotes, I for immediate addressing. Now look at the code that got generated. D00048. Is the 48, is the 0048 the address of where the H is stored? Yes or no? No, it is, the 48 is itself what? The ASCII code for H. It's part of the instruction. Yeah.
Why would you ever not do that?
Really good question. Why would you ever not do that? Because in a typical program you have variables.
But you need like a get.
And yes, and so a variable has to be, like a global variable has to be stored at a fixed location in memory because its value will change. So you see, this is only good for special purpose situations. And that was an excellent question, but you understand the deal. Yeah.
So in the block that you have like four hexadecimal digits that you can use to like depict something, right?
Oh, you're right. You are right. In other words, this was
It's 0048.
It's 0048, and notice that whenever you give a single, whenever you put a single quote around a single ASCII character as the operand specifier in assembly language, it puts it in the right half.
So does that mean that you can store like two ASCII
You
characters?
actually could.
Would it print out as two ASCII characters?
Well, no, because when you do because remember, the way you output a character, an ASCII character, is store byte. And you remember that store byte always takes it from the right half. That was a really good question. That's a good observation. Yeah.
Oh, it takes it from the right.
When you do store, okay, so you understand that this instruction right here, this F1, FC1, 6, is the store byte accumulator, and it always stores it from the right half. And so here, let's go ahead and single step through this and we'll see how it works. Okay, so we'll single step through, and so here, boom, see there's the 0048. Are you with me? Okay, and that's 72. And now so that's load byte accumulator here, and then store byte accumulator, there's the H, and then boom, there's the I, and then stop, and boom. So that's the demo. Okay, so that's immediate addressing. Now, next thing we want to take a look at are these trap instructions that are only available because of the operating system, which is between the level ISA, the raw machine, and the ASMB5, right? So it's 5, 4, and 3. So the operating system is at level 4. So now these are some really handy instructions. So the first one is decimal input. So the assembler knows that this is a trap instruction, and it uses the mnemonic DECI for decimal input. The opcode is 00110, so there is no register R field, but it can have any addressing mode, addressing AAA field. So what that does is that converts a string of ASCII characters from the input device into a 16-bit signed integer and stores it into memory. And the decimal output instruction is deso, similarly, except instead of inputting it from the input device, it outputs a 16-bit signed integer from memory into a string of ASCII characters and sends that string to the output device. And again, there's no register R field, but there is a register AAA field. And now here's another instruction that is a super important one. This is called the unconditional branch instruction. Now what we're going to do with this instruction is this instruction is going to allow us to put all the globals at a fixed location in memory at the top. So you know how cumbersome it is when you put your data at the bottom, how you have to count down and it changes, blah, blah, blah. Well, what we're going to do is we're going to use the unconditional branch instruction as the very first instruction at address 0000, and what it's going to do is it's going to branch around the data. So what does an unconditional branch instruction do? What it does is it causes the next program statement to be executed to not be the one that's immediately after the branch. Are you with me? Now take a look. What is this language called with the PC left arrow? What is that language?
Register transfer language.
Register transfer language. And what does this register transfer language say? What happens? The program counter gets the operand. Now, how on earth does that make things skip around? Oh, rats, we're in this. Can you zoom in here? Okay, look. What's the von Neumann cycle? Fetch. Decode. increment. Actually, increment the what?
Program count.
The program counter. And this is fetch what? Instruction from where? Fetch from where? From mem what? Yeah. I'm constrained here. Okay. So fetch from memory and then decode and then increment the program again, and then what? Execute. And then what? Repeat. Now look, you guys, if you can see this, you will, this is crucial. But I think you can get it. Look. You fetch the memory, you fetch the next instruction to be executed from, and the program counter is the address in memory of where you fetch it from. Right? Then what do? You decode the instruction. And then what do? You increment the program counter. Why do you increment the program counter? Because you want to make it do what? Why do we want to increment the program counter? So the next time you fetch from the next one. But now what happens if during the execute part, the execute does what? Does what?
Oh, increments the PC.
No, not increments. Just changes it. Just replaces it. Then when you repeat and you go back to here, what's the instruction that's going to be executed next?
The address that you specified.
The one that you said it's going to get from. Now, does everybody see that? That's crucial. This is how it works. This is how branch works. Does everybody get it? Okay. So yeah. So because this is wired in, this von Neumann cycle is wired in, and so if fetch, from the location of memory specified by the PC, so that's where you get the next instruction. You decode it, you increment the program counter, so hopefully that next one will be executed. But now if the statement that you fetched happens to be an unconditional branch instruction, the BR, that stands for branch, then what it will do is it will change the program counter. So when you repeat and go back to here, it's going to get the next instruction from whatever the branch instruction changed it to. Does everybody see how that works? All right. So now here, yeah, question?
Is there a general rule of thumb on how much data or like memory storage the unconditional branch instruction leaves?
That is that is completely up to the programmer. Is there any kind of limit? And that's the programmer. You can replace it with anything. It's unrestricted.
And is that specified in the instruction specifier? How much data we're leaving, or
No, not how much. No, the only thing that's in the instruction is where do you want to go to get the next instruction?
And that's the okay.
There's nothing about how much or where. It's just where you want to do the next. Yeah.
So you would have to put this instruction first, then the variable,
And then
then the rest.
That's exactly right. So the point is you'd put this in, because we know that programs are always loaded in the PEP9 system starting at 0000. So we'll just have an unconditional branch, and then we'll branch around our data, and then, yeah. All right, really good. So let's take a look at figure 5.11. So look, in figure 5.11 what we have is branch to where? 0x0005. Oh, now, here's the thing. There is no, it looks like we have forgot to put the what? Comma what? Comma the addressing mode. Now here is just a little shortcut. So with the branch instruction, if you omit the addressing mode, then by default the assembler assumes that it's immediate. Okay, so BR default mode is immediate. So you don't have to put, and it's so common that we never put it down, but you can put it down and it'll still work. All right, so what this does, so let's take a look at what figure 5.11 does. It does branch to 0x0005. Now what is at 0x0005? What is at address 0005? The what? The decimal input instruction. And what did it do? It branched around the storage for one integer. And notice that we allocated. Now what does the dot block instruction do?
It
Allocates how much?
2 bytes.
In this case, because of the 2, it allocates 2 bytes of zeros. And so that's enough to store one integer. All right? And then what the next instruction does is it does decimal input from where, from the input device and puts it where? At what location? 0003 addressing mode? Direct. So that puts it there in that dot block region. So does everybody see? And then deso does what?
Prints it out.
It prints it out. All right? And now the next whole long list of things is what? It's
Space plus.
load byte accumulator space plus space 1 space equals space. And then what?
Print out.
What's at 0035? Load word accumulator. So that takes the number that we stored there. Are you with me? And then what? What do we do?
Add.
Add accumulator. How much? 1. But what's the address? Does that mean we go to location 1 to find out where to add it?
No, it's
It's immediate addressing. So we can add 1
what's that?
0003.
to what's that 0003. And then what does the next one? Store word accumulator.
So store the sum.
So store the sum back at 0003 and then print it out
In decimal.
in decimal. And so here is, on this next part of the slide, if the input is negative 479, then the output is negative 479 plus 1 equals negative 478. It sounded like we were all following this. Let's demo. Okay, so here's our demo again. Let's go to figure 511, copy the source, and let's build it. Okay, so see how nice all this is? Gives us, there's our listing, and there it is. And so let's go through this, let's go through this one at a time and check it out. So first we'll branch to, oh, and by the way, notice that negative 479 here is in our input. So we'll single step through here, boom. So notice how we branched. Does everybody see how we branched? Yeah, question?
So by doing that, all that achieved was like, it skipped over the instruction at like 0003?
Yes, but notice you said the instruction at 0003. It's actually not an instruction, it's actually data.
Right, okay.
Yeah,
Dr. Wolford?
yeah.
You might want to clear the memory because it says in the accumulator.
Oh, you're right. Let's stop this and let's go to the clear memory and let's build this again and let's start debugging.
If you didn't have that branch there, the program would just stop once you hit 000.
Oh, that is a really good observation. If you didn't have that branch to 0005, then that 00 would be interpreted as the stop instruction, and it would just stop. That was a really good observation. Now you're thinking like a machine. That's good. Yeah. Does everybody see? So now watch. We'll single step through here. So now watch when we do decimal input. Boom. Now, how do we know, that was decimal input into what location? 0005. Now, here we can see what's in 0005 here. If we go, oh, we need to scroll up to the, see, so if we look at see, look, here at 0003, right? So this is 0, 1, 2, 3. So it's FE21. Now, do you agree that FE21 is probably what? Is probably what?
Negative 479.
Negative 479. Yeah. Everybody see that? Okay. And so now as we single step through this, So there's the negative 479. That was the deso. Does everybody see that? And then space plus 1 equals in negative 478, and we stop. Yeah? So that's that demo. Okay, so is there a question? More questions? Yeah, Chase?
Can branch statements be put anywhere in the code?
That is a really good question. The answer is yes. The assembly language is unrestricted. There's no types other than binary in a machine, and it just the von Neumann cycle will crank away, and whatever it happens, that's what happens. Yeah, no restrictions. Yeah, it's a lot of power, but with power comes responsibility. Okay, so do you have a question?
Nothing.
Okay. Okay, now it gets better. Another instruction, trap instruction that's provided by the operating system is the string output instruction called Stroll. Now here's the way Stroll works. What it assumes is that you have stored an ASCII string of characters somewhere in memory, but you got to make sure this ASCII string of characters is terminated, has to be terminated with the 00 byte, the null byte. Are you with me? And what it does is the operating system, when you call this string output instruction, the code actually goes through and it, starting where you tell it to start, it outputs that character and then the next one and the next one and the next one. And each time it outputs it, it checks to make sure it's not the 00, the null character. And it keeps doing it, and when it gets the null character, it stops. So it does all of that in a loop. So you don't have to write a loop, and you don't have to write those statements individually. So here's how to use it with this next one. So here's figure 5.12 is the same as figure 5.11. But now, check it out. We don't have to do those ASCII characters one character at a time. So look, we start off the same as we did before, branch to 0005. All right, and so 0005 is our deci and our deso. But now look, now what after the deci and the deso, what do we have? String output. Now this string output says string output from where? Oh,
001B.
001B using what addressing mode?
Direct.
Direct. So that means 001B is an address. Is everybody clear on that? Because it's direct addressing, that means 001B is an address. So you go down to 1B, and what do we see at 1B?
202B.
Yeah, the code is 202B20, but what is the source code, the assembly language code? Dot ASCII. Okay, so that's a sudo op dot command, and that stores the string space plus space 1 space equals space. But now we have this bash x00. Now what do you suppose that is? Inside of a double quoted string, bash x00 is how you write the null byte.
So that it interprets it as a pair of integers and not a pair of ASCII zeros.
It interprets it as one byte. Anytime you have a bash x and then you have two characters, and it's inside a string, the assembler will generate 1 byte of what you tell it to generate in hex.
Because of that X.
Because of the /x. By the way, you guys, you can do this in C++. You can do this, as well as in assembly language. This is a standard way to do it. Okay. In fact, you know what you could do? You could do any character that way. And like, for example, instead of writing the plus, what is the plus? What is the hex for plus? Can you tell there? What is the hex for plus? Come on.
2B.
Yeah, 2B, right? Is everybody clear? So what you could do is you could say, instead of where that plus is, you could say, you could replace that plus with bash x2b. And it'd still work. The assembly language code would be the same. Does everybody see how that works? And we could demo it, but I think you can see it. I mean, you trust me that it will work. Is everybody clear on this? And now, so we're moving right along. And now the next one that we're going to look at is the hexadecimal output instruction. And here again, this is another trap instruction. Okay? So with the hexadecimal output instruction, and again, there's no register R field, but there is an addressing AAA field. The mnemonic is hexo for hexadecimal output. And now, as with deso and deci, this operates on one word. So now, how many bytes is in a word? 2 bytes. And how many hex characters is in 1 byte? How many hex characters does it take for us to specify 1 byte? 2. So that means that hexo must output 4 characters. Does everybody see? Because it's 1 word. So all of these quantities and however they all fit, we all know these by now, right? Okay. So it converts a 2-byte word from memory into 4 hexadecimal digits, and it sends the string to the output device. And again, this is a trap instruction. So now here's an important point. Dot commands set bit patterns at assembly time. Okay, so what does that mean? Dot commands set bit patterns at assembly time. So you see, let's go back here. Do you see that dot ASCII? What did that dot ASCII do? That
Change the
yeah,
characters.
to the 202 blah blah blah, right? And what did that dot block do? That generated those 0000.
2 bytes of 0.
2 bytes of zeros. Does everybody see? So that when does that happen?
When you do a dot.
Well, I know, but when did it generate that code? When we did what?
When you build it.
Yeah, yes, when we assembled it. Remember? That's when we assembled it. Okay?
So it translates it into
It translates. That's a translation step. The dot commands happen at translation time. That's a translation step. Executable statements interpret the bit patterns at runtime. Now look, there's nothing to prevent you from generating a bit pattern one way at assembly time and have it do what? When you execute it, interpret it how? As differently. This is a huge point. You understand what we're saying? There's a difference between translating it and getting it ready to run and then running it. Are you with me? Does everybody see? Now this next program illustrates this. Let's see if we can predict this, what the output of this very complicated looking program is in figure 5.13. First, what do we have at address 0000? Branch to where? 0009. Now look. Now let's take a look. Actually, we're not going to have time to run this whole thing through, so we'll just set it up for next time, for tomorrow. And we hope we're back in the right room and all the equipment works. Okay? So, so now what is that? What does dot word, how many bytes does dot word always generate? Always generates 2 bytes. Because it's dot word and a word is 2 bytes. So everybody see when you say dot word 0xFFFE, that generated the FFFE? You see that in the object code column? And how many bytes does dot byte always generate? 1. So did you see that dot byte 0x00? That's 00. And how about the dot byte capital U?
the 55.
That's the 55. Now, what do you suppose that 55 is, if you looked it up?
The ASCII.
The ASCII. You want to double check that? You better double check it. Might be wrong. And what about the dot word 1136?
That's 0470 in.
It's 47.
Yeah, that 1136 did not have a 0x in front of it, so the assembler says, oh, that's a decimal value, converts it to the proper binary and hex and generates that code.
That's done by the assembler.
That's done by the assembler at translation time.
Because when you run it, the instructions, there's no.
Now, when you run it, the program has no idea where those bits came from. All of that is ancient history.
Just interpret everything as binary.
Yeah, but depending on what the instruction is. So now, when we say deso 0x0003, what do you suppose is going to come out?
The decimal number at 00.
Yeah, and what's it going to be? Can you tell? FFFE. Yeah, look, it's -2. Where the heck did the -2 come from? Well, during assembly time, it translated 0xFFFE to FFFE. But then during the run time, during execution time, what is that statement? Deso. What does decimal output do? Interprets it as a decimal number and outputs it. So look, there's no -2 here, but look where it comes out. -2. But we understand now the difference between what happens at translation time and what happens during execution time. And what happens first? Which one happens first?
Translation.
Yes, and so let's close with figure 5.8. We'll continue analyzing that program tomorrow. Let's close with figure 5.8. So 5.8 shows that there's always 2 runs. The first run is translation. So you take the assembly language program, the application in assembly language program, the assembler translates it to machine language, right? Then that machine language program is loaded into memory and executed. At that point, all that translation stuff, where it came from, the dot commands, all those dot commands are ancient history. It's just binary. And then, so the second run, it actually runs the application. Are we good? All right, good deal. See you tomorrow. We're going to have to cut a lot of this stuff out. Ah!